So let's go ahead and get started. Thank you for coming to the last of the GRE sessions. We're going to be really talking about some sort of miscellaneous topics that the GRE throws in that you probably remember, but may not remember how to do. So we're going to try to break it down a little bit. And I'm going to give you a couple examples, some of the weirder things they can do with it on the GRE. So again, we're talking about the quant section still. So our 2, maybe 3 quant sections is what we're really dealing with here. So the first of these is this difference between permutations and combinations. I bet you guys remember those terms, but you may not necessarily remember how to do these types of problems. And if you do remember, you probably remember there's like some kind of like weird thing with an exclamation point, or you might remember an NPR function or an NCR function. We don't need to actually do that. And in fact, factorials are difficult to do on the calculator that you have for the GRE anyway. So let's look at a way that we can deal with these types of questions and actually distinguish between them on something like the GRE. So first off, there's 2 ways I can ask this question. What is the difference between these 2 questions? They are distinct from each other. In what way are they distinct? The order in which they end matters in the case of which one of them? The one on the left, the order matters because we care who comes in first, who comes in second, who comes in third. So if I have it go A, B, C, is that different or the same as C, B, A? That's a distinct difference because there is a first that gets gold, a second that gets silver, and a third that gets bronze. So in one case, Alice gets the gold. In the other case, Alice gets the bronze. That's a different result. On the other question, the order doesn't matter. So if the first 3 people is A, B, C, or C, B, A, are those the same or are they different? That would be the same thing because it doesn't matter what order they're in, it's just the first 3. So that is the difference between permutations and combinations. How do we calculate these things? How do we differentiate between these calculation-wise? Well, then they both actually start out the same. What I do with these problems is I draw in 1, 2, 3 spots because the question is about first, second, and third, or first 3 people. So I'll draw out 1 spot for each person. And how many people can come in first place? Five people. But now that I've already put one of those people in place, I only have 4 people left for the second place. And then once I have those 2 people placed, I only have 3 people left for the last place. So it's going to be 5, 4, 3. That's not any different between these 2 setups. It's the same on both sides. Now, this answer should be bigger or smaller than the answer on the right. Which answer has to be bigger? The one on the left or the one on the right? The one on the left has to be a bigger answer because there should be more distinct ways to do it first, second, and third than there is just combinations over here on the right. So what we end up doing is we have to divide by something to shrink down the number of combinations on the right side. So what we do is we divide by the spot in which they place. So we divide by 1, 2, 3. 1, 2, 3. First spot, second spot, third spot. That's all you really have to remember to do to figure out this question. So what is my answer on the left? If I multiply these out times, how many different permutations are there? So there's 60 ways in which people could finish in this race. On the right, how many ways are there? And here's where you should be working a little smarter, not harder. I can cancel some things out here, can't I? 3 and 3 cancel. 2 cancel, so I'm left with 5 times 2, which is just 10. And the reason I want you guys to do that is to cancel terms out is sometimes these numbers can get very, very large. And it's easier if you just get rid of some of the numbers before you start calculating, so you don't have to do division and look for common factors and all that kind of garbage. It's just easier to cancel out. So there's 10 ways for 3 people to finish the race. There's 60 ways for 3 people to finish the race first, second, third. So what I do is I have this little phrase in my head. If the order matters, or sorry, if the order does not matter, I don't divide. If the order does matter, I don't divide. If the order doesn't matter, I do divide. If the order does matter, I don't divide. If the order doesn't matter, I do divide. It's a little weird, but it's, to me, it's like my version of a mnemonic device. I've never yet found something that works better than that. Does everybody understand the difference between these two problems? All right, now let's switch it up a little bit. So we're gonna go a little off script here, and I'm gonna add an extra slide here. If I can, I should be able to. Well, I guess I'm gonna have to do this to do it. I'm gonna work from within here. Can you guys see the slide again? Okay, so let's change the question up a little bit. Let's say they give me something like a question that says this. There we go, text box. Lucy has 6 pairs of pants, 12 different rings, and 3 different blouses. How many different outfits can she wear if she wears 1 ring on each hand? And so notice they're leaving a little bit for you to figure out, because how many pairs of pants can a person wear at one time? Just 1. And how many shirts or blouses can somebody wear at one time? Just 1. So they had to put a limitation on rings because somebody could wear 10 rings. And they'll do this where they'll limit the choices that you have. So what kind of a setup would I do for this? Well, what I would do is I would create myself 1 line for pants, 1 line for shirts, 1 line for, or 2 lines for rings. 1, 2. All right. So for pants, how many possible pairs of pants could she wear? 6. All right. How many different blouses could she wear? 3. How many different rings does she have to choose from for her first finger? Or first hand? 12. How about her second hand? How many rings for her second hand? 11. Because she's already worn one. She's already chosen one. So this is our setup for now. Does the order matter? Unless otherwise stated, you should assume the order does not matter. They didn't give us anything here to make me think that I should deal with the fact that she's left hand or right hand. It just says she wears one ring on each hand. So the order does matter. So even if the order didn't matter, like 6 and 3 isn't going to change. You divide those by 1, whatever. But if she wears one ring on the left hand, one hand on the right hand, that's the same as wearing it on the other hands. That's at least what we're going to assume. And that's actually the level of assumption that the GRE is going to make. So if the order doesn't matter, what do? I do divide. So I'm going to divide this one by 1. And what I'm going to divide the second slot by? Let's look at our previous example. What do we divide each slot by? The number of the slot. Yeah. So divide the next slot by 2. So what's my answer here? Is there anything that'll cancel out? I could cancel my 12 and my 2, make that 6 and 1. And what's my math after that? What's my final answer? I'm going to pull out a calculator. You can too. Times 3 times 6 times 11. 1188 is my final answer for this question. 1188. So sometimes they'll give you these multi-slot kinds of questions. Sometimes they'll give you the single, like one set of slots. Here's another good common one. Here is, let's get another text box out here. A sundae bar has 3 flavors of ice cream, 6 sauces, and 4 toppings. How many different sundaes can be made from 1 ice cream, 1 sauce, and 2 toppings? Is this any different than the last question? Or is it just different numbers? So is this a different question than previously, or is it the same question with just different numbers? It's not even more restrictions, actually. I gave you it's literally the same question because I didn't have to give you the restriction on pairs of pants or blouse because we can at least assume that. In this case, they had to put that restriction on it because otherwise I could have 2 types of ice cream or 3 sauces or something like that. But really, this is the exact same setup as we had before, except how many different flavors of ice cream can I choose from? Not 6, but 3, how many types of sauces can I choose from? Not 3, but 6, how many toppings do I have to choose from? 4, and then what in my second choice? 3, and my second slot would be divided by 2. So it's literally the same exact setup, and a lot of these questions do have the same setup, except just have different numbers. So what's my final answer going to be here? 3 times 3 times 4 times 3. 108. All right. Now, I'm going to introduce to you the last special type of question we have here. And this one is particularly devious. Particularly devious. 12 people are sitting around a circular table. Actually, let me do it smaller so I don't have to deal with such big numbers. 6 people are sitting around a circular table. That actually is a very important point to this question. How many ways can they be arranged? How many ways can they be arranged? So first off, let me ask this question. Does the order matter? Yes, 100% yes. Especially because it's a circular table, the order matters. Because with a circle, we've introduced the concept of something you guys have all feared from organic chemistry if you took it, chirality. We've introduced chirality into it. So right-handed is different than left-handed. So that's one thing you got to think about here is you're not just going to do this problem once. You're going to do this problem how many times? You have both right-handed and left-handed, so we have to multiply the answer by what? 2. This is due to the fact that right-handed and left-handed combinations are different than each other. So if I go A, B, C, D clockwise and I go A, B, C, D counterclockwise, those are different from each other. Oh, chirality. It's the bane of my existence. Now here's the other problem. How many slots should I have for this problem? How many seats are going to be at the table? 6. Because it's a circular table, something annoying happens. How many people can sit in that first seat at the circular table? Exactly. Thank you, Kushraj. You don't know where to start. There is no first seat at the table. So therefore, only one person can sit in the quote unquote first seat because that one person defines the rest of the problem. Oh, so this is a circular table problem. Your first seat is one person. One person starts it. So how many people can sit in the second seat? How many people are left after that one person sat down? 5. And then at the next seat, 4, and so on. 4, 3, 2, 2, and 1. So What is my final result for this thing? How many for just one direction, clockwise, say? Five times 4 is 20, times 3 is 60, times 2 is 120. But how many for both clockwise and counterclockwise? My final answer for this has to be 240. So what's the key word that's in here that tells us we have to do this weird stuff? Circular table. So anything that's arranged in a circle will require this extra level of weirdness. So you got to start with your first spot with only one person or one thing, and then you have to multiply your final answer by 2 to deal with the circular table problem. The GRE doesn't do it a lot, but you do want to be prepared for this one, because where's this going to show up when you're scoring in the 140s, the 150s, or the 160s? The 160s. When you're in the 160s, if you're that's where you run the risk of getting a problem that looks like this. Then all of a sudden, boom, that's one more question you know how to do. So hopefully that you'll run into one of these guys and actually know how to approach it. If it's a squared table, I don't have to multiply by 2. No. It's a very funny thing, because clockwise and counterclockwise start to lose their meaning on squares. So circles are weird. Circles are definitely weird. All right, now let's transition out of there. Let's talk about probability. Probability. So probability is the number of outcomes divided by the number of desired outcomes that you're looking for divided by the total number of outcomes. Let me shift back to presentation mode here. Bing. And let's share that. There we go. So probability of an event, number of desired outcomes divided by the total possible outcomes. So why did I cover combinations, permutations first? Is because sometimes combinations, permutations might end up being your denominator here, because it's total possible number of outcomes. So what if I ask this question? What is the probability of drawing 0 aces without replacement? And what does that without replacement mean? Why would they add that in? Sometimes when you see magic tricks, but yeah, so you're basically removing a card every time. Because sometimes with magic tricks, you'll see them say, take a card and then put it back into the deck. That's with replacement. This is saying take a card out and it's out. So the number of cards in the deck has now gone down, which will change the way the probability is calculated. So what's the probability of drawing no aces when drawing 4 cards from a standard fair deck of cards? Why are they writing this? Standard fair deck of cards. Or standard and fair, I should say. What is that phrase in there for? What purpose does that serve? I will say it's a boilerplate, basically. Does it affect the way you solve the problem? Yeah, it means that it's possible to pick any card equally. So you'll see them do things like that with, if they're talking about playing cards or dice or something that's an object of chance, they'll say it's standard and fair, so that there's no, like, you can't argue that there's, oh, a 6 on the die comes up more often than a 1 comes up or something like that. Basically, standard fair is their boilerplate way of saying, just treat it like you're supposed to treat it, darn it. So let's figure this out. let's do the math. What is the probability of drawing no aces when drawing without replacement? 4 cards. So first card, second card, third card, fourth card. So how many cards could I pull in the first pull to get no aces? What is my total possible number? I.e., how many cards are not aces? And if you don't remember, decks of cards are 52 cards. 52 cards. Yeah, you want to make sure you're familiarized with a deck of cards. So 52 cards. Basically 1 through 13 in 4 suits, although it's ace through king. So there's 4 aces total, which means there's 48 cards that are not aces out of a total possible of 52. So what's my next probability that's going to go into this? How many cards are left that are not aces? $47, and how many cards are left? And so on and so forth. 46, 45, 50, and 49. So here's where the calculator is your best friend. So pull out a calculator. You can use your cell phone calculator. What is this probability? 47 times 46 times 45 times, or divided by 52, divided by 51, divided by 50, divided by 49. And what do we get? And you should get a decimal. In any good probability question, you should get a decimal. Agree or disagree? We got 1.72. I agree as well. I get 0.718 or 0.72. 72% or 71.8%. Okay. Now, sometimes it's easier to do a calculation instead of direct like we just did. Do it indirectly by figuring out the complement of an event. And the complement of an event is saying, okay, if I know the probability of one thing happening, then the probability of the exact opposite thing happening is going to be 1 minus that probability. So a complement is the opposite. So what's the opposite of drawing no aces? What's the complement of drawing no aces? And the reason I'm asking this, it's a little tricky. At least one ace. But what does that actually mean if we think about it? What does that actually mean, at least one ace? Does that mean drawing 4? Oh, it does. Drawing 4 is at least 1. Does it mean drawing 3? It does, because drawing 3 is at least 1 ace. Does that mean drawing 2? Yes. Does it mean drawing 1? So if I wanted to calculate this probability directly, I would have to calculate the probabilities drawing 1 ace, drawing 2 aces, drawing 3 aces, and drawing 4 aces and add them all up. Do you want to do that? No. So that's why you want to watch for opportunities to do the complement. Because what's the answer to this question in one simple step? So what is the answer to this question? $0.282. Whoops, that's a 2. I'm going to say that's a 2. 0.282. Because if I know the probability of drawing none, then the probability of drawing at least 1 is going to be the opposite, the complement of that process. So when you see phrases like at least in a probability question, what should you be looking for? When you see at least in a question like this, what should you be looking for? The complement. Yeah. Because if I see that at least, I got to know that it's going to be harder to do that. At least questions require you to do a lot of work unless you just use the complement. So it's a pretty good thing to pay attention to. Now, we were assuming these were and probabilities, like the probability of drawing 1 ace and then another ace and then another ace and then another ace. There is a difference in the phrasing of probability questions, the way they're written. You can have different ways of saying things. So you could say, what is the probability of drawing something and something, something or something? And this is also an or question. The last one, what is the probability of drawing an ace or red card, but it's a special kind of or. So we have to know all 3 types of our probability rules. And if you were in biology class, in genetics even, actually in genetics, you probably learned these rules, right? Why are these rules important in genetics? Yeah, if we're calculating probability of illnesses, or if we're doing anything with like Punnett squares, these were questions they would ask. These are like straight derivatives from that. They're not going to do it in biology terms on the GRE, but it's very analogous to that. So what is the probability of drawing a 1 and a 2? All right, so they're telling me a 1 and a 2, which means I'm going to do what with those 2 probabilities? I'm going to multiply them. So what is the probability of drawing a 1 and a 2? So what's the probability of drawing a 1? Oh, and I should clarify with replacement. I forgot to add that to the question. With replacement. So what's the probability of drawing a 1? 4 out of 52. With replacement, what's the probability of drawing a 2? 4 out of 52. Because I put that original card back in, So there we go. And what am I going to do with these two individual probabilities? I'm going to multiply them because it's an and question. So my final answer is 16 over 52 squared, or I calculated it out to be 0.006. There we go, 0.006. All right, what's the probability of drawing a 1 or a 2? Well, this is what's called a mutually exclusive or. Because now, this is going to sound weird to say it, but bear with me. Can you pick a 1 and a 2? Can you pick a 1 and a 2? Or sorry, let me rephrase that question. Can you pick a card that is both 1 and 2 at the same time? That's what I mean. Can you pick a card that is both 1 and 2 at the same time? No, you can't. 1s are 1s, 2s are 2s. So 1 and 2 are mutually exclusive, as we say. They cannot overlap. So we're gonna do the same thing, 4 over 52 and 4 over 52 for my 1 and my 2. What do I need to do with these probabilities? I'm gonna add them. If it's a mutually exclusive or, you add them together. So that would be, I did the math and we've got 0.153. Much higher chance. Does that make sense that if I say or, it should be a higher probability than if I say and? Does it become more likely when I say or does it become less likely when I say or? Or means more likely. So if you've got an or question, you should always be thinking it's got to get bigger. It's got to get bigger. If it's an and question, it's got to get smaller. All right. The last one is a case of not being mutually exclusive. So can I have a 1 that is also red? Can a card be 1 and red at the same time? Yes, it can. So now I have to do something a little different. I got to figure out the probability of one, the probability of the other, and the probability of both together, the and situation. Because if it's both red and 1, is it or? No. You can't, according to the way this is phrased, it can't be 1 and red at the same time. So we have to take those situations out. So first off, what's the probability of being a 1? Four out of 52. What's the probability of being a red card? How many red cards are in a deck? Mm-hmm. 26 out of 52. And then how many red 1s are in a deck? Two. So 2 out of 52 are red 1s. So let's calculate up this probability now. So it's going to be 4 plus 26 minus 2 over 52. So 28 over 52, or 0.538. And there you go. And again, or should probably be a higher probability than normal. So if we're picking a 1 or a red card, and red card's far more common, yeah, I should see a pretty large probability there because about half the deck, well, literally half the deck is a red card. Now, will it always be decks of cards? No. In fact, the GRE has tended to stray away from decks of cards. And there's a reason for that. Because culturally, decks of cards might not be culturally open to everybody. Like, how many people here have never played a game with a with standard American playing a set of deck of cards? I would imagine that there's going to be at least a few. You all have? Well, good. But because it could be a potentially culturally biased thing, we've been seeing there's a tendency to stray away from decks of cards and dice and more into things like a chance cube. Like, seriously, I've seen that on tests. A chance cube is rolled that has a 1, a 2, a 3, a 4, a 5, and a 6 on each side. So they're not calling it a die. They're going to describe it as just a chance cube. That's very possible, but you still would treat them in much the same, well, in exactly the same fashion. You got to watch out for the and, the or that's mutually exclusive, and the or that's not mutually exclusive. In fact, I believe that's called the XOR, if I do remember my logical terms, and don't quote me on that, but I think that's XOR. All right, so any questions about doing permutations, combinations, and probability kinds of questions that you might run into on the GRE? How many folks think this is the fuzziest stuff that we talked about so far? Like, it's been probably your weakest at this. Well, that's good. I usually find a lot of folks are really not remembering probabilities and permutations, commutations all that much because there's not a lot of usage of it outside of it. Like, the only time you really did probabilities was Punnett squares, most likely, and those are pretty basic compared to some of the stuff you're going to see on the GRE. So yeah, this is something you want to try to dig into a little bit more. Make sure you understand how these probability things work. Yep, and it's just it's just so little application in your daily lives that it's hard to recall these skills. So it's something to practice with the permutations, combinations. I really encourage you guys to try the slot method like this instead of using formulas, because it really does just make it a simpler, now it's like just sort of filling in the blanks kind of question rather than to remember how to plug things into a formula. The hardest part is probably deciding, is it the order does matter or the order does not matter.